video. As promised, in the second part, we will go through an example. And in this example, we are looking at a simple 3-bus network as shown over here. So shown in the figure is impedance value on each of the line. So these impedance are in per unit value. You are given the real power and the reactive power of bus 2. Over here, this is what we call the scheduled power. You are given the real power of bus 3, the scheduled power. And you are given the magnitude V3, but you are not given the delta, the phase angle of V. You are given the magnitude and phase angle of bus 1. You are not given the V2 and delta 2. So the objective of the solution over here is for us to identify what is the P1 and Q1 and also the Q3 over here, because they are the missing part here. They are the power flow that we are trying to find, whether they are injecting into the network or coming out from the network. But to do that, to solve for the P1, Q1, and also the Q3, we are going to use other information. We are going to solve for other information, and in turn, the solution of that other information will help us to determine the missing P1, Q1, and Q3. So what are those? Those will be V2 and delta 2. We are going to find V2 and delta 2 and also delta 3. When we found that, then we are able to use their information to determine the missing powers. Why? Because we are given P2 and Q2. If you know P2 and Q2, you can use them to estimate V2 and delta 2. If you know P3 over here, you can use them to estimate delta 3. Okay, we will see next how. So the first thing is we should convert our admittance. Okay, we should convert our admittance. We should convert our impedance into admittance and put them into a matrix as such. So you should be familiar with the concept of self-admittance and also the off-diagonal over here. And then you want to form the 3 known power flow equations that are given to you. You are given, remember, P2, P3, and Q2. Okay, P2, P3, and Q2 are given to you. So we want to form the power flow equations of P2, P3, and Q2. How do you form them? You form them according to the generic power flow equations that I show over here, which I also pull it out from part 2 of this video. So you form the power equations of the known power, the scheduled power, okay, the known power. And then, because you're able to form the power flow equations on P2, P3, and Q2, you can also determine their Jacobian equations, meaning you're able to find the partial differentiation of P2 against all the unknowns, which is the V2, delta 2, and delta 3. You're also able to find the partial differentiations of P3 against all the unknown, which is the same, that is V2, delta 2, and delta 3. You are also able to find the partial differentiations of Q2 against the same unknown, that is V2, delta 2, and delta 3. And because each equation have to perform 3 partial differentiation, you end up with 9 partial differentiation equations, such as like this. Okay. Now, the question comes whether you should do the partial differentiation yourself or should you memorize the partial differentiation equations that were given to you in part 2 of the videos. If I can show you quickly, is it here? Okay, whether you should memorize this, whether you should memorize this or not. My recommendation is you should not memorize the partial differentiation equations that is shown to you over here. Although you can memorize them and use them on any other network, but it is not advisable, because if you try to do so, most likely you will end up with a lot of errors due to remembering wrong informations, and then with the numbers of variables that you are seeing over here in all the 8 equations, I don't think that we can be able to memorize them without mistakes, yeah, when we try to apply them later on. So my recommendation is, don't memorize the partial differentiation equations, but perform them yourself. It's not difficult, yeah. You simply have to perform the partial differentiation of the 3 equations that you can form over here against the 3 unknowns. All right. So the next step is, recall that you are given the scheduled power in bus 2 and bus 3. Well, you can go ahead and convert them into per unit value as well, such as shown over here. So just let's assume that the base value of the complex power is 100, so we divide them with 100. And the common practice is, if the real and the reactive power is flowing away from the bus, we put negative, as shown over here. And because P3 is flowing into the network, we put positive. Okay, now we are ready to apply our Newton resonance. Before I do that, all right then. So the first step of the Newton resonance method is, we want to remember, before we do that, remember your purpose now is to identify the value of V2, delta 2, and delta 3. From there, we are able to use them to calculate the power flows of bus 1 and bus 3. They are the only 2 buses without the complete power flow values. So you want to estimate, okay, the value of V2, delta 2, and delta 3. So we begin by assuming a value for that. So initially, we assume, for voltage, we normally assume with the value of 1 per unit. And for delta, we normally start with assumptions of 0. 0 what? 0 radian. Okay, not 0 degree, yeah? It's 0 radian. That reminds me that you should be aware that the theta angle for all the emittance over here are also in radians. Okay. Then, with the initial assumptions of V2, delta 2, and also delta 3, you can apply these 3 values into the power flow equations, the initial 3 power flow equations that we form. This one, yeah, the P2, P3, and Q2. So if you apply these 3 values that we assume into the 3 power flow equations, you obtain these 3. You obtain these 3 values. Okay, this is what we call the P20, P30, and Q20. The 0 over here is to notify that it is the initial assumption. Okay, and this is the scheduled power value that we are given. So we find the difference. So the purpose is to get the difference that is as small as possible. Okay, ideally 0. Ideally 0. And you can also apply these 3 values that we have assumed into the 9 Jacobian equations that we have formed. Okay, 9 Jacobian equations that we have formed, and put it inside this matrix. Okay, so how do you arrange them? It depends on how you arrange the unknown. So if we arrange the unknown delta 2, delta 3, and V2 as such in this order, and then this value is obtained from the equations of partial differentiations of P2 and delta 2. This is the partial differentiations of P2 and delta 3. This is P2 and V2. Okay, and then this is the P3 delta 2, P3 delta 3, P3 P2. This is Q2 delta 2, Q2 delta 3, Q2 V2. Okay, so the differentiation against what, in what order, it is depending on how we arrange our unknown over here, the order of the arrangement. And whether this row is for P2, this row is for P3, this row is for Q2, how do we know? It depends on the order of arrangement for this one. If we arrange P2 as the first one, P3 as the second one, and Q2 as the second one, then this will be for P2, this will be for P3, and this will be for Q2. Okay? So, from here, we are able to determine this because we can form three parallel equations from this matrix. And from the values we determine for these three, okay, after we obtain them, these are the change of the delta and the V. You go ahead and add these three values with the initial three values that we assume for them, which is this one, and then we will obtain the new value for them. So as you obtain the new value, you want to repeat the whole process. And remember what you need to do. What you need to do is take this value now, apply inside the same three power equations to obtain a new value for this one, and determine the new difference. When determining the new difference, the scheduled power remains the same, yeah, because this is given to us. So with the new power difference, we put them into the matrix over here. And then with the new with the new values of delta and V, we can also determine the new value of the Jacobian equations. And we put inside the matrix. After that, we want to determine the new change. And from the new change, after we obtain them, we add them with the new values. We obtain a newer values, okay, such as this one. Okay, you obtain the new change. From the new change, you add them, okay, into the new value just now. This one, the new value, with the new change, add them into the new values. You get a newer values, like this one. And then the whole process repeats. Okay, the whole process repeats. So this delta 2, delta 3.2, and V2.2, you apply back into the initial part here and repeat the whole process. And then the process repeat and repeat. And for this equation, for these problems, the solutions converges in 3 iterations. So how do we determine the convergence is by determining that the mismatch of the power, okay, the mismatch of this power. When the mismatch of the power, the smallest one is less than a certain threshold. The largest one is less than a certain threshold. So this is a mismatch. Okay, this is a mismatch, and this is a mismatch. So the largest in terms of magnitude, yeah, we ignore the sign. So the largest of the mismatch is less than a certain threshold. Then we consider that the process have converges. The process have converged, and then we say that our solution is final. So in this case, the maximum mismatch is less than this value of threshold. And then with this mismatch that we have obtained, this is the final value for V2 with the magnitude and also the phase angle. And V3, the phase angle is this one. This is the magnitude that we were given earlier in the problem. Okay, so in other forms of questions, various threshold might be given to you. It might be slightly larger so that you don't have to solve or repeat the process as much, or they might want you to only solve it for a certain number of iterations, okay, depending on the questions. So one iteration, this is one iteration. So from here until the end of here is one iteration. As you repeat second iteration, then repeat third iterations. Okay. So as you obtain the final V2, we have the complete value for V2 now. We have the complete value for V3 now, meaning we have the magnitude and phase angle. And from there, we are ready to determine what is the power values, the real and the reactive, for bus 1 and also for bus 3. Okay, if you recall, bus 1 has no value at all. We are not given the value for P and Q. We are not given the value of Q. So you go ahead and form the power flow equations for P1 and Q1 and also Q3. Okay, the way they are formed are the same as the way we form the P2, Q2 and also the P3 over here. So we form the equations for P1, Q1 and Q3. And because we have obtained the values of V2 and V3, and then we know what is the value for V1, we can apply them all inside here, and then we will obtain the value for P1, Q1 and Q3, such as this one. Okay, so that will be the complete process of a Newton-Raphson method. So as you can see, that given even a simple 3-bus network, the process is rather long. And the process is rather long. I would say there are many opportunities for mistakes in the calculation. So in order to avoid yourself from being exposed to calculation mistakes, you have to be very familiar with your partial differentiation. And you have to be very clear with what you are doing, at which iteration you are at. In other words, you have to be very clear with the iteration process of the Newton-Raphson method. Okay, and also you have to be very comfortable in dealing with matrix multiplications. So this is something that you want to refresh yourself again if you're not familiar with the mathematical operations of partial differentiation and also matrix multiplications. So that will be the end of this this chapter. So if you have any questions, feel free to contact me. You can send me an email or send me a message to my WhatsApp number. I think that will be all. So I hope to receive feedback from you all, and I will contact you again. Thank you for tuning in.